All right, everyone, welcome to today's lightning lesson. We're going to be talking about optimizing search and data processing with self-hosted SLMs. Doug Turnbull and I are really excited to host Daniel Svanava today from Superlinked. He is fantastic. He's very bright, very smart. We actually, in the last cohort of our AI-powered search course, had him as a guest instructor, and the class was very excited and had a lot of takeaways. It was one of the most energetic discussions we had. So really excited to have him today to talk about some cool stuff that he's cooking up over at Superlinked. Today is the second of a series of talks we're doing as part of a free series called Exploring Modern AI Search. Over the course of the next week, starting yesterday, today, and then going into next week, we've got a bunch of speakers and topics. So, again, yesterday was Nathan from TurboPuffer talking about searching 100 billion vectors in object storage. Today, we've got Daniel. And on Monday, we have a session about agentic search, the big deal about agentic search. What is it with Doug and I? And then you can, we'll post a link in the chat in just a little bit so you can find a link to sign up for all of these if you're not already signed up for them. But agentic search we'll be talking about Monday. And then we've got three additional sessions next week. One with Andreas Wagner from Search Hub, where we'll be talking about whether we're all doing information retrieval wrong. We're going to have kind of a candid discussion about some things that we're, as an industry, doing right and some things that we're maybe not doing as well. Then on Wednesday, we're going to be talking about modern AI search techniques you should know. And then on we start our course next Thursday, but next Friday, we'll be doing an AI search fundamentals course on vector spaces, matching, and ranking. It's really intended for people who are taking our AI powered search course to be able to, maybe come up to speed on some of the core information retrieval skills. But it's public and open to everybody if you want to join us. So these are the remaining sessions over the next week. We definitely encourage you to sign up, get kind of a taste of what the course will be like, as well as learn from some of these amazing search experts like Daniel today. So I did mention the AI-powered search course. Real quick plug for that. We start next Thursday, March 5th. If you're interested in the course, it's a month-long cohort-based learning opportunity with Doug, myself, and a bunch of great guest instructors. This time we've got Daniel Wrigley from Open Source Connections, we've got Connor from Weaviate, we've got Radu from Vespa, and we've got Mr. Query Understanding himself, Daniel Tukelang, who will be joining us. We've got an amazing cohort of students from many top companies. If you're interested, please sign up. There's a QR code there if you want to check out more, but we'll post the links. You can check those out on your own time. Like I said, it's a month long, sort of both deep dive into particular topics as well as a broad coverage of all the latest and greatest AI search techniques. So definitely check it out. And if you're on the Lightning lesson today, we have a discount code you can use for 20% off. The promo code when you go to sign up is small LM for small language model, or you can read it as SMA LLM, but that's not correct. Either way, there's three L's, and if you want to take advantage of that, we'll post a link here shortly. So with all that being said, I'm really excited to dive into today's topic on optimizing with small language models. So Daniel, I will hand it over to you, and I'm excited to get going.
All right. So Smolum for the coupon. I like
We
it.
call them small LLMs. I don't know. I don't think it'll stick.
Um, well, one man's small is another man's big. We are still talking about a couple billion parameters, even
Fair.
for the small ones. Well, thanks for having me. I'm a little bit sick today, so I think it's gonna be a collective effort for all of us to get through the material. I would love to perhaps hear from folks in the room as well. Maybe I'll give a few shout outs here and there, and folks can also kind of contribute. I like to learn something during these talks, so that's the best way to do that.
Good. Daniel, do you
And
prefer people post their questions in the chat, or do you want them to just raise their hand in Zoom, or what do you like?
maybe they can just raise their hand, and if we have too many, then we can kind of batch that in the chat. I think.
All right. Sounds great.
All right, cool. Okay. So Let me just pull up. I did make slides for you all. So this is a special treatment. Um, all right. Uh, so I'll dive right in. Raise your hand, or if you are shy, then uh, post your question to the chat, and then I'm sure Trey will flag it for me.
For sure.
So I think we had the intro. I think my goal today would be to, first of all, if there is somebody in the room still kind of fully running on managed large models and managed, APIs for embeddings and re-rankers, that sort of thing. My first goal is to kind of show you that there is another way, maybe talk about the benefits of self-hosting and using open source models for search and the data processing that happens around search systems. And and then we'll talk about kind of how to do it. And then yeah, if there are any questions, I'm happy to kind of jump on those. Okay, so first of all, just like a fun stat, maybe not everybody knows this, but um, basically, there are more than 2 million open source models on Hugging Face. By the way, if somebody is looking for a project improving the model search on Hugging Face, natural language search, kind of describe a problem and get some models back, uh, I would love to sponsor that project. But because there are like over 2 million models there, and most of them with very permissive license, and people are sleeping on that. Actually, this chart was created at the end of 2025, I believe, and it ends at 2.2 million models. And I just took a screenshot this morning, and it's 2.6 now. So there is like clearly more open source models being produced than like the rest of us know what to do with them. Um, and I think it's a huge opportunity. Of course, not all of them will be amazing, but they're there, and for the most part, they're free. Um, and I think when people think about open source models, they sort of think about some kind of compromise that they would have to do if they went open source. And I really like this chart from artificial analysis, where basically they plot on some basket of benchmarks the best proprietary model and the best open weights model over time. And basically, what you should take away from this chart is that it takes, 1 to 3 months of waiting for the frontier kind of open source model to catch up with the frontier proprietary model. So you don't do anything, you wait 1 to 3 months, and you get basically the best performance that's available on the LLM side. So it's not really a huge compromise. And just kind of zooming into just to get a taste for how that looks at the really cutting edge. Um, let's say over the span of kind of end of November to now. So let's call it 2.5 months, right? We had basically here, this was Opus 4.5. I think it's this bump over here. And GLM5 kind of matches that on this particular basket of tasks. So it's really not like some kind of huge concession that you take. And by the way, this is the most competitive kind of part of the market, right? This is the general kind of reasoning, big LLM models. And even there, the open source stuff is at most, 3 months behind. Everywhere else, actually, it's doing way better, right? And in many cases, by switching to an open source model that's task specific or has kind of more features, you are actually improving your performance. So this is really the worst case for the most competitive part of the market. So it really shouldn't feel like a concession to explore open source models. Um, and yeah, basically 2.5 months apart in terms of the release date between Opus 4.5 and GLM5. Um, and I wanted to give people some kind of taste for what's happening in these kind of latest and greatest giant open source models before we kind of then scale back and talk about the small models. Um, Maybe you saw a headline, GLM5, 744 billion parameters. Can't really imagine self-hosting that. That sounds like a nightmare. Sounds like 50 to 100 H100s sitting somewhere, right? This is like not something that you want to bother with. But because it's a mixture of expert model, like it's very common these days. I think there are 256 experts in GLM5. For any given token, only something like 40 billion parameters actually activate, right? So basically, 40 billion parameters of that model allow it to be on par with Opus 4.5, right? And 40 billion parameters is something we can imagine, right? Like at FP16, that's 80 gigabytes of memory. Um, of course, yeah, I'm like the sleight of hand there is that these are kind of automatically selected from the much bigger pool based on the query and the token and everything. But I think it's my point here is that it's not sort of totally different universe, right? Like these are the first of all, the proprietary and the open source models are basically on par, and the largest open source model in terms of like active parameters is actually not that many parameters. So this is not like too crazy stuff, right? In terms of one day being able to quite easily host even the biggest open source model. But and then by the way, same 200K context window between Opus 4.5 and GLM5 as well. So the only thing that GLM5 doesn't have is the multimodal capability of Opus. Um, you know, all of that said, basically, that's kind of the capability and the engineering on the largest models. The like second small detour is into the commercials because I find the commercials of this to be quite interesting as well. So we have a model that's sitting out there free, and you just have to pay for GPU, self-host it, and you can run it for free. I think it's like MIT or whatever is like very permissive license to use. And at the same time, there are these companies that run sometimes slightly better model for you. You pay per token, not per GPU. And OpenAI, I think August last year was doing 13 billion per year, and this January they announced like 20 billion yearly revenue, right? So that's quite interesting, right? Like somebody is making $20 billion selling people kind of per token inference, while at the same time there is a model that's like pretty much the same, that's free, and you just have to pay for GPUs. The delta there, of course, is like one or two orders of magnitude difference in price, right? If you pay for the GPU versus per token. So this should sound like big opportunity that companies can unlock by self-hosting, right? Get a huge discount. But also for businesses still, everybody is doing inference seemingly, but that's because there is just a ton of value still to be created and captured in that space. So that's just kind of broad context of what's happening in the world of kind of open source models and inference. And the good news is that actually you don't have to run inference for 700 billion parameter model to solve specific tasks. And this is where we get to the kind of small models. So basically, small models is anything from like, let's say, embedding model. Embedding model, think about it as something that generally only performs one forward pass. So you put some tokens on the input or image patches, and you kind of find the embeddings of the tokens and run it through some kind of neural network kind of once, and you aggregate the kind of embeddings that fall out of that computation, and maybe you aggregate them into like a single dense vector, or you keep them kind of as a set of vectors, or there is a way to kind of collect them and make it like a sparse vector at the end. But generally, that computation is very efficient and is a single pass through the network. So that's kind of on the easy side, right? It could be like low hundreds of millions of parameters for these encoder models. And then you have other kinds of models, small models that are useful. And that's for example, lots of folks are building knowledge graphs these days. So processing a bunch of documents extracting, OCRing text out of them, extracting information, answering questions for each document, extracting named entities and relationships between them. Um, for all of those tasks, you can use task-specific small models. Again, sort of up to, let's say, 8 billion parameter models. And the trick is, combining a couple of these models together to solve, these sort of use cases. Um, and then when we talk about hosting or kind of running, executing these models, that's when it gets much easier, right? Because you have a couple billion parameters, which means that the whole model, both in terms of weights and in terms of memory it needs for inference, like additional memory, comfortably fits into GPUs with like 16 to 24 gigs of RAM, right? Which is the stuff that's super easily available in your cloud provider. And maybe for context, at Superlinked we have been building these AI-powered search systems for the last couple of years, and we kind of reflected on what is the bottleneck in delivering let's say a RAG system or some kind of search tools for agents or natural language search for humans. What is the kind of limit to scaling such system, to improving the accuracy of results? And we somehow always come back to inference, because the small models, right, the kind of models that I have on this slide and many similar ones, are not exactly very important for the big inference providers because they make money hosting the GLM5, right? They're all kind of competing for hosting the big models. That's where they make money. They don't care about the late interaction, whatever vision capable embedding model or re-ranker, or some of these NER models or relationship extraction models, and that's why those models don't get supported or it takes super long. You see these models shoot to the top of the benchmark, and then maybe it takes months or never for those models to be supported. That's kind of on the proprietary inference side, and we work with a couple of those folks. Um, on the open source side, there are some options. There is Tay from Hugging Face. There is Infinity, which is, I believe, an independent project. There is FastEmbed that started at Quadrant, right? We have few of these projects that um, focus on this type of models useful for search. But none of these is really sort of like somebody's main focus. Like there isn't a company that exists only to provide that thing. Similar to how there is SGLang and VLLM and all of those big projects for the inference for the big models on the open source side as well. And we have put together a bunch of different stacks with Tay and Infinity, on serverless GPUs like on Modal, or our own kind of stack within Google Cloud or AWS. So we have basically, that's a long way to say that we have been building these systems at scale, 1 terabyte plus kind of vector search indices. And we have always cobbled together the solution for inference. And sort of second half last year, we decided to actually look at the problem more closely and see if we can do something in that space and kind of solve the problem once and for all. And the moment one of these search models or information extraction models shoots to the top of a benchmark, like next day it gets supported. And that's what I wanted to talk about today, sort of like how to build such a system and what is it that we are kind of bringing to the market. And that whole thing will be Apache 2.0 open source, so I have like nothing to sell you here. Yeah, I would like to kind of talk about what does it take just to be able to use those models comfortably, and then we can go into kind of the stage 2 of this process, which is once you figure out how to discover the right open source models, then you bring them into your stack, you can run them easily, and then from there you can improve them, right? Which is like the other thing that's not available in the proprietary world. You can do continued pre-training, you can do fine-tuning, you can do LoRa's. you can do you can optimize the instruction for the instruction following models. So we can get into some of those topics as well. But people sort of way underappreciate the models that are already out there, and that's why I always make it a point that like, hey, let's just sort of start using some of those kind of millions of models that are available in open source.
Hey Daniel, a bunch of
Mhm.
people are commenting on how
Mhm.
awesome this slide is, just like summarizing everything together. So kudos on this.
Mhm.
One question I've got is obviously new models are coming out all the time and changing, and there's benchmarks and what have you. I'm curious how often you have to update this slide, or if this is like the set of recipes that you go with, and you just sort of upgrade to the newest version of
Right.
these. Like how
So,
dynamic is this?
most of this slide is obsolete. Um, BGE-M3 is um, not a current model anymore. Interesting aspect of that model is that it can, in one inference, produce three different representations of data. One, like a single dense vector, sparse vector, and multi-vector representation. But otherwise, it's not the really state-of-the-art model by any means. So, you know, if you, I think you will have to go kind of just chasing the benchmarks is pointless if it doesn't translate into meaningful impact on your project, right? And so I think it should be sort of instead of being stressed about, oh, new model, let's switch to it. I think it's useful to figure out what is your kind of business goal, what is the metric that, are we, there are not that many metrics, right? There's basically, do we want to reduce cost next quarter because we want to do we want to index way more data, or we are already indexing a lot of data, handling a lot of queries because maybe we kicked off some agent initiatives and realized that agents do like 20 queries each time to figure out what's happening. So is it basically cost and kind of cost efficiency? Is it quality? And in quality kind of territory, switching to a better model, if you have an easy way to switch, it's sort of like a no-brainer, right?
Mhm.
Um, if you have, you need to do, ideally, you need to do something on the eval side to kind of convince yourself that even for you, it's a better model, not just because of, somebody said so. Um, but worst case, you do some A/B tests in production, and you I've seen like big companies sort of like roll out things quite. I don't know if there is a term for this, like vibe evals or what, but
Yeah.
um, um, yeah. At the end of the day, I think we should lower the barrier to being able to switch these models and upgrade the models, and then sort of just go with the metrics. So cost, quality, and then the third one that I think is interesting is basically some version of either security or reliability or compliance. Basically, how much of a control do you have over your system, right? Um, and all basically, I think like somebody in your company should decide like which of these three is the focus of the given quarter, and then being able to quickly check out, what are the top 1 to 3 candidates for the various models you want to be putting together to launch a project, see what's on top of benchmarks, and then just kind of quickly iterate and launch. So this slide basically you should just read it as um, some examples of how you can combine different models to um, solve with small models a problem that maybe you thought you need a big model for it, but if you
Mhm.
split the task and sort of use the right tool for the right job, you can do better because you don't have to. If you have a task specific model, you don't have to prompt it as hard, right? It already
Mhm.
has been trained to extract named entities, so you don't have to say please extract named entities, right? And then there is the adaptation part of this, right? Which is if you have an open source model that already in the community got trained on legal domain or financial domain or medical domain, right? Then you don't have to put into system prompt sort of like the sort of foundational understanding of domain and kind of like what's really important for you. And again, that's savings and it's kind of more predictable output. So domains and then languages. We deal with companies in Japan and other countries that the the proprietary models, and be it, embedding ZD rankers, LLMs, they have to be sort of the lowest common denominator in a way across tasks and across languages. And then, it takes a lot of effort to prompt them to kind of isolate the task that you want within the capabilities of the model. And still you may not get a very good performance, and you are paying 50 or 100x more than you could if you had a
Mm,
task specific open source model.
for sure.
Okay, so yeah, think about these small models as kind of puzzle pieces, and you are kind of putting those puzzle pieces together to build your projects. Of course, you still maybe need a proprietary model for kind of the overall, let's say, reasoning step, but a lot of the data processing and, of course, all the kind of search related topics, as I said, knowledge graph construction, that sort of things, you can just have task specific models. And maybe just like a small fun example, just to give you an idea of how narrow some of these models are, and therefore they can be really good for the task. For example, there is a whole community that produces models that do OCR on receipts, right? Um, and imagine that you are on a team somewhere in a big enterprise, and you are doing this kind of expense tracking system, and you are wrestling whatever it is, Gemini Flash, kind of VLLM, right, with the vision capability to kind of parse data or answer questions on top of receipts. And in the meantime, there is a model that's fine-tuned specifically for receipts, right? And that model probably saw more receipts than the data set of certainly more annotated receipts than the Gemini training data set. So um, that's just an example. Okay, so a couple different projects. In terms of like the kind of next part of this, um, basically, yeah, I wanted to so I kind of established that you can build these projects from some collection of models, and so what kind of remains is where do you run these models and how do you kind of not go crazy telling your platform engineer, hey, can you provision me a worker with this or that model? I need to test stuff, right? Like, how do you contain the complexity of basically this like long tail of the model landscape, right? So instead of sort of worrying about one or two models, now you have to worry about a bunch of models, and you want to run them. Uh, you want to maybe isolate the workloads. You want your system to be compatible with many models, hundreds of models, and you want to do it efficiently. So this is kind of like one of the most annoying kind of janitorial tasks that you can imagine. Um, because just to give you an idea, to basically run inference for a model efficiently, um, you basically take the model, and what is a model? Model is code and weights, right? Basically. And that's why sometimes it's open weights because you don't have the code, right? And so here we are talking about open source models. So you have the code, you have the weights. But to run the model efficiently, you basically have to rewrite all the code and you just use the weights. You have to basically hand optimize all the code to get like 10x throughput improvement for a given GPU, something like this, versus whatever the implementation is in, let's say, sentence transformers or one of these libraries. And so if you want to support hundreds of models, now you are like rewriting the code of hundreds of models. I mean, they're not all like unique, right? So maybe you'll have we have, I think, at the moment, maybe 35 different kind of model adapters, and that those are the implementations, and then they get parameterized for the different models. So this is like basically janitorial task on kind of collecting and rewriting and optimizing that code. And before coding agents, this wouldn't be a feasible project for a startup. But luckily, I can talk a little bit about our process that we use to kind of solve that problem. But basically, it's all about benchmarking. So having a reference implementation that delivers reference quality on a bunch of benchmarks, and then if the model is supported somewhere, you can run the somewhere and get the performance like tokens per second, latency, and then you have target tokens per second, the quality on a given set of benchmarks, and then you can just run agent on a VM somewhere rewriting that forward pass of the model and kind of banging its head against the wall until numbers, go up and numbers look good. And you can have, one of these agents sort of doing that for each of the models you want your inference engine to support. And then you get something like what I'm about to describe. Um, so basically, I mean, to run inference for all these models, ideally you self-host in your, AWS or GCP, and the kind of atomic unit of the system is the worker, right? It's something that starts on a VM somewhere, gets access to the GPU or GPUs, and then has to kind of manage the different dependencies of the different models. Um, should be able to load the model into the GPU memory, should be able to receive requests and aggregate the payloads from the request and form a batch of data that then can be run through the GPU kind of efficiently. Um, and ideally, to switch between the models, you don't have to reload the worker, so you can kind of have a least recently used kind of eviction mechanism for the models. And if you want to serve LoRa's on top of this, so kind of these adapters that kind of focus the model to certain set of capabilities, which is more and more popular these days, you kind of have to do this management of loading the LoRa's on top of the model and evicting them and so on. In Yeah, our approach is basically depending on the model, we either kind of rewrite the forward pass directly in PyTorch, or we wrap one of the existing open source execution engines like SGLang. And sometimes for the reference, we use sentence transformers or kind of the model creator reference implementation, so we can A/B test them and stuff like that. So this is the worker, and it's just like a Docker image that you can start on a local machine or on a cloud VM. Um, I mean, CPU only is possible, but NVIDIA GPU is because it can be like L4 or A10, these kind of like lowest, oldest set of cards. We recommend using those. So that's kind of your first problem. You need this kind of worker running somewhere. And then the second problem is you want to kind of do the infra around the worker. So in our case, we chose Terraform. We chose Kubernetes for the cluster itself, and we'll distribute the whole sort of cluster setup as a Helm chart. We'll distribute Terraform modules for preparing your AWS or GCP account to kind of receive or start the cluster. And basically, we want to sort of auto scale. You want to have a router on top that understands the state of the workers and sends the requests to where the workers have the model loaded in memory. And if you are doing like sort of generation, then it's useful to also make this aware of the KV cache available at the different workers. So the router has to kind of the router that sits on top and decides where the request goes benefits from not treating the worker as a black box, but understanding kind of what's happening in the worker. And yeah, like we added some features to this that help the caller, the client side, to, for example, be able to create worker pools to isolate, let's say, your pipeline workload from your query workload. Because normally, you have a couple teams building these systems, and they all provision their own infra to do all this processing with small models. And that's kind of unnecessary if you have one big cluster that can support and kind of lazy load all of these different models. And if the users can kind of isolate the worker pool so they don't steal each other's resources, then the platform team or like whoever is taking care of your infra only has one Kubernetes cluster to watch and babysit, basically. Maybe just as a fun fact, like for the folks in the room that already ran kind of self-deployed setups around some of the frameworks that I maybe mentioned previously, when we talk to companies who do that at scale, my favorite question is, what is their GPU utilization, basically? And that could be a fun poll to do here in the room for folks who run, let's say, search related models or small LLMs in their own cloud, in their own deployment. Do you know and are you willing to share what is your average utilization of your GPUs? Maybe you can put that in the chat. I would be very curious. And I think it's also useful to see the other people's numbers because then you can benchmark how well you are doing. And you know, are your GPUs sitting there sort of largely unused? You are still doing better than paying somebody else per token, probably, right? But still, maybe just to make you feel better, it's not uncommon that we talk to companies spending, you know, tens of thousands per month on GPUs or more, and having sort of average utilization of sort of 1 to 3% of those GPUs. And that's, you know, specifically for inference workloads, right? Because those tend to be spiky. Companies tend to not share the GPUs between kind of the query load and the pipeline load and the training. So typically the numbers are pretty bad.
Daniel, is that because people aren't scaling up and down because they've just pre-allocated? Like, I'm curious why the
So
inefficiency.
so the elastic aspect, yes, that's one. The other one is that typically people load like one model per worker. So you
Hmm.
basically say like, hey, this is going to be a GTE modern bird worker. And then, you know, every second you don't want to process your tokens with GTE modern bird is the second you are not doing anything with the GPU. Which is why, you know, for the worker side of things that I mentioned here, it's, you know, it's really important that part of loading multiple models on the same GPU, and then just, you know, receiving the workload, and once the model is kind of loaded in the GPU memory, you can just instantly run inference for each of those
Hmm.
models basically, and you just have to kind of evict once you start running out. But if you have, you know, let's say low billions or hundreds of millions of parameter models, you can put four of those on L4 with 24 gigs of
Hmm.
VRAM, right? And then suddenly four different people can be using the same worker as opposed to four, right? So that's it's like easy 4x right there. But then, you know, the more you kind of do that, the more you have to be able to kind of see the demand coming in and kind of scaling the workers and not letting those people kind of kill each other, basically.
Hmm.
So, and then the other thing is that if you run unoptimized code on the GPU, the utilization can be high, but your tokens per second or latency can be a disaster, right? So, and you know, over here in the surge land, like we care about latency, right? It seems that uh, folks in the LLM land or agent land are okay to wait, you know, tens of seconds. But then, you know, those agents maybe go from tens of seconds to minutes if their search tools are slow, right? So at
Hmm.
some point, it sort of comes back to fast, right? Fast is good. And for tasks like parsing different elements of a query with some kind of NER model, or you are identifying, hey, there is some filter intent here. You typically have kind of low tens of milliseconds for that, and for that you want like, you know, as optimized implementation of the sort of model inference as possible. Okay, so basically, you know, this should take sort of one Terraform apply and one Helm install to get up and running. And a lot of it then happens over the API, so it's kind of user friendly in terms of targeting different hardware with different queries and creating those resource pools. That sort of thing is all over API. Okay, and just to kind of make this a bit more practical, by the way, if there are any questions, just feel free to jump in. Um, what I have next is a couple examples of, you know, when we were on this slide, I said that one way we think about the different capabilities of these small models. We think about encode, score, and extract as, you know, kind of the building primitives. And part of the work of creating this product is conforming all the different models to the same API. So you have encode, score, and extract. Score is re-ranking, but also scoring for, you know, not safe for work or kind of toxicity, other kind of instructions. It doesn't have to be re-ranking. And then extraction models are notoriously, they all have very different API, right? How they give you back the extracted data. And all of this is multimodal, right? So all of these kind of take item which can have text and images and other things on it.
Daniel, while you're
Uh,
back on the slide,
mhm,
Bala earlier had a question about where'd it go? Can you throw some light on how re-ranking happens using models?
mhm,
We are gonna next week. We've got one of our talks is on AI, modern AI search techniques you should know. We're gonna talk a little bit
mhm,
about crossing coders and re-ranking processes.
mhm, mhm,
Obviously,
mhm,
in the course, we'll dive deep into that as well. But I don't know
mhm,
if you wanted to touch on that
mhm,
briefly.
mhm, mhm. Definitely. So, you know, typically when you are, you have some data set and you want to find relevant set of items for a query, um, you you kind of want to in the first step find good candidates for those results very quickly, right? Because maybe you have like millions of those documents, and we use these like vector embeddings in that phase because we can build an index that in milliseconds helps us by indexing the data as these vector embeddings, and then we turn the queries into vector embeddings. We do similarity search for those vectors, and maybe they're sparse, maybe it's vector sets. But basically that happens very quickly, and maybe we get back 50, 100, 200 potential results. And then, sometimes it's worth it to spend some more electricity on whittling those 200 things down to 20 things. And to do that, we can use these re-ranking models that basically take the query, take the candidates, maybe one by one or in pairs, and you ask a question, hey, for this query, how relevant is each of these candidates? And sometimes the model is set up to always just look at the pair of query document and it produces a score, 0 to 1 of how relevant it is. Sometimes it looks at pairs of candidates and a query and says this result from the pair is better than this other one. So there are different sort of setups. But this is a much sort of higher fidelity way to understand the match in terms of kind of the textual sense of relevance, right? Um, and yeah, then you just need to run that model somewhere. And this adds latency, right? So that's always the trade-off. It adds compute, so spend, and it adds latency because it has to happen as a step two after you have collected the candidates from the index. One last thing I'll say, which I think is very cool, is that even in the open source, we have re-rankers now that are trained to follow instructions. So basically, when you will be using this inference product, uh, many models now, in addition to let's say taking the input to embed or the item query sort of data sets to re-rank or score, or doing the extraction, in addition to those inputs, they take the input of instruction where you can kind of describe what is the overall goal, for example, right? Or give additional, sort of like a system prompt, but it can be case by case, right? Based on other sort of context of that specific query. And I find that people totally underestimate how they can improve their retrieval quality by tuning that instruction. Think about it as like mini fine tuning, basically, right? Because instead of kind of bringing some examples and refining the model, that's kind of what we do in fine tuning. You can kind of refine the instruction. Yes, it's gonna, the model will have to parse that instruction every time it runs the inference. So it's makes it like a little bit slower, let's say. But it can boost the quality by quite a lot if you tell the model kind of what aspects of the ranking you care about. So kind of instruction following re-rankers, I think we now have many techniques like GEPA and other approaches for optimizing these instructions. I definitely recommend folks looking into that. And this used to be kind of like Cohere, I think, launched the first instruction following re-ranker, like, a year ago or whatever. And that used to be like, wow, use proprietary re-ranker because it has been tuned to follow that instruction very closely. You have a lot of that now in open source as well. Just kind of further to my point of um, open source gets you there maybe just a bit slower. Okay, so just to like make it a bit practical, I have a couple examples here of what I mean by encode, score, and extract. So it's sort of, I guess, what you would expect, but by the way, this product will have Python and TypeScript SDKs. So if you are building your application backend in Node.js, you'll just be able to kind of self-host that cluster, and then on your application side, just use a TypeScript SDK to talk to it, or Python SDK, and roughly this is how it will look. And so for encode, we generally mean turning data into some form of embeddings. It is the BGM3 model that I mentioned that in one encode pass gives you dense, sparse, and multi-vector representations of the input. We have, of course, various image embedding models, and those image embedding models typically take text or image or both on the input. So you can search with text into images, and vice versa. And then, nowadays, I think late interaction and multi-vector representations are kind of, that's when instead of having single vector, single set of coordinates to represent your whole document, you have hundreds and sometimes thousands of vectors to represent the document. And then on the query side, you have basically vector per query token. And then you are doing kind of a set distance, like kind of all pairs distance. And, those models are super efficient for their size and the quality they give, because they don't have to funnel the smartness through like single vector representation, but they can kind of be much more expressive in that multi-vector sense. And obviously for us, that's a big focus to support all of those. And by the way, those can be vision capable as well, right? So I think that's like really the cool stuff in document search or question answering is basically instead of doing OCR and pulling text out of documents, you can feed screenshots of documents into vision capable multi-vector embedding model, get hundreds of vectors per page, and then search directly in those representations. So this keeps the images and the text content kind of all contextually together. Actually, if we get like a couple minutes, I wanted to show you kind of how that looks in practice. But let me just run through this. So we have the score, right, which is basically you just have your query and you have your items. As you can see, query is also this item, so it can be multimodal. And then you just get scores for all the query item pairs. And then together that would look something like this. So you would have stage one, where you would do the retrieval, and then stage two, where you would do the re-ranking of the retrieved candidates from your favorite vector database. So that's kind of what you would expect. And again, you are using one cluster to run all of these models, auto-scaled, efficient, and you can switch them in and out, experiment, and make good progress. On the extract side, I mean, named entity recognition is kind of the basic, but for example, you have something like Apple CEO Tim Cook announced the iPhone, whatever, and you want to extract person, organization, product, location. There are also relationship extraction models where you basically define the types of relationships you want to extract, and or you do sort of classification where the extraction is basically labels, class labels. And then we have like you can extract text from images, which you can call kind of image captioning or OCR, or even kind of question answering, right? So, for example, for a document, you are like a screenshot of a contract, you are asking what is the total amount of that receipt or contract. And it's sort of all conformed to the same API. Let me just so these are like the value props that we are building this thing for, but basically that's what I was kind of describing the whole time. So I don't think we have to like really go through those. I wanted to just maybe go through some benchmarks. Um, you know, this is kind of like the basics, but I'll say it because I think still some folks maybe are not super clear on what's going on. So probably many of you have seen the MTAB, the embedding leaderboard, where this is kind of where the journey of selecting an embedding model starts. I really recommend going into the tasks. So I think it's really useful to understand what are all these different tasks. So these are data sets, right? Like the data and the queries and the sort of correct results. And the performance on all of these tasks averaged all together basically is what gives the model the score. But when you look at the tasks, you'll realize that these tasks are very diverse, right? This is like medical and finance and some specific language, Romanian, like it's a bunch of different stuff, and I think it's really useful to be able to sub-select the task that you actually care about, like hey, medical retrieval for certain kind of images, right? And then look at the performance of the model on the task. And that's not just for embeddings, but for any kind of when you are trying to figure out which open source model to use, right? So just to give you like some sense, this might be too small, but here is a task, right, that you might be looking at, and kind of our friend Hamel Hussein, look at the data. This kind of like applies here as well, right? Basically, this is how a benchmarking task looks, right? This would be an example of a document. So this is some kind of breast cancer, whatever, medical data set, and then we could look at queries, and the queries look something like this, right? So this is an example of a task from that benchmark, right? And it looks very different from like this kind of task, right? So this is also medical. I see MRI here, which is fun. But I think this is kind of more broadly kind of scientific. Um, but yeah, also medical, and then okay, I have legal, right? So this is like completely different domain. These are some questions around what is and isn't legal to do under some set of contract. Um, and and again, like the problem that you are probably trying to solve doesn't look like all of these tasks combined. And so therefore, I wouldn't look at the combined score for these models on this benchmark or other benchmarks, but I would look at performance on specific set of tasks. And that's also much easier than creating your own evals. And it's, I think, a good starting point. Like just figure out, okay, here are the 3 benchmark tasks that we actually that approximate the problem we are trying to solve well. And then here is a quick example for that vision capable multi-vector set of models that we also support, where that I mentioned that instead of doing OCR and pulling text out of the document and then doing textual search, when you have a query like where is the S3 single point receptacle located, that model is doing basically um, uh, like vector search over text embeddings of screenshots of these pages to find the result. Okay, I think we could kind of keep going. There are sort of hundreds of these benchmarking tasks, and they are relevant based on kind of which of these models you are looking at. One thing we want to sort of make a bit easier when we release the product is to help people select the right model. We keep hearing that this is one of the biggest bottlenecks and pain points. Hey, like, sure, you give me 200 models, but which one should I use? So we want to kind of create some kind of way to understand what is in these individual benchmarking tasks, find the task that kind of looks like the problem we are trying to solve, and then on that task have ranking of the models we support together with the performance on different hardware, right? Just to kind of know what to expect. And that can be anywhere from embedding models doing like 50 millisecond, 50 percentile latency latency and pushing, 50,000 tokens per second on NVIDIA L4 to, let's say, 5 times slower than that. So maybe 5 or 10,000 tokens per second, and latency is like half a second, that sort of thing. And again, same for re-rankers, extraction models, and all kinds of other model types that we will discover people actually want to use on the small model side. Okay. And I guess my call to action from all of this is that, so this was sort of like a preview, right? Preview for, so that's a typo. Preview for this product that we'll be bringing to the market, so you heard it here first on Trace and Dax program.
Breaking news.
Breaking news, but
Heard it here first.
still hopefully kind of contained within the enthusiast community. What we would love from the community, of course, is feedback as always. The product is not sort of out there, so you will not find it on GitHub, you will not find it on the Helm child registry. But nevertheless, we are working with a couple folks and some companies for private testing, and we even sponsor some of these projects. So if you have always wanted to, let's say you are doing the course and you wanted to do some sort of project, right, to kind of graduate out of the course, and let's say you wanted to rebuild the Hugging Face search because you know it, or maybe archive.org search, or some kind of document parsing exercise. I don't know if we want the certain files released by the U.S. government recently. That could be a mess. but there might be other files that the U.S. government released that you want to experiment with. We want to sponsor inference and also maybe some kind of symbolic sponsorship on top for folks who experiment with our product, build this project that they always wanted to build, and give us feedback. So I think that's my call to action. If this was interesting, you want to learn more, you can follow me on LinkedIn, and before long, I might be back talking to you. But yeah, I think that's all I
Yeah,
have for today. Maybe we can do a couple of questions if
yeah, for
folks
sure.
can do. Yeah.
Yeah, I know. So we're at the top of the hour, so I know some people have to drop. A few have already dropped, but if you want to hang around for some questions, if you have some, or if you just want to listen, yeah, we'll go for a few minutes, see what people have. I've got a few, but actually, yeah, I'll let people raise their hand first, and if not, I'll dive in. Dishan said, please share the QR again if you would, Daniel.
Yes. So that's I think that's my LinkedIn, because basically like connect to me, and if you can DM me the project that you would want to do, search project, data processing project, we basically take it from there. So we sponsor it, we give you the resources. But I think this is just my LinkedIn. Let me double check. This is like QR code has this kind of property similar to vector embeddings that if you just look at it, you can't tell what it represents, right?
Yep. All
Okay,
right.
I see in the chat mention that late interaction models require large disk usage for storing the token vectors for the documents. That's true, but as you have maybe heard in the TurboPuffer talk yesterday, they just slashed their prices by 94%, I think. So that generally databases based on object storage benefit from kind of the cost efficiency of object storage. And there are ways to optimize this kind of multi-vector search. Maybe you don't need all the vectors that these models produce. There are also techniques for compressing these vectors in various ways.
Yeah.
Actually, our product also comes with this MoveEra
Mhm.
algorithm, which takes the multi-vector representation back into single vector, but that sort of arguably defeats the purpose, right? So you can also do single vector and then use the multi-vector models for very efficient re-ranking. That's another sort of idea.
And just a quick plug, one of the sessions in the AI powered search course is actually with Connor, shortened from Weaviate. He's going to go into Movera, how it works and how you can leverage it. So Yeah, it's interesting. My intuition is the same, Daniel, that, well, if you're just mixing the vectors, you've got a spectrum, right? From a single vector describing a whole document to a separate vector for every token, and then you can kind of go anywhere in between by merging. So yeah, my
Hmm.
intuition's the same, but the
Hmm.
stats, at least in the research papers, show that you still preserve a lot of the value even when you kind of pull them together. So I don't know.
Hmm.
Jury's out.
And and that's the thing, like it doesn't have to be. So when we sort of launched it officially, we'll have a merged leaderboard. For example, merging the multi-vector retrieval models and the sparse, Splade v3 and friends, and the latest single dense vector models. And then the rerankers are graded on top of this on the same set of tasks. So that's one problem of MTAP is that the benchmarks for rerankers don't actually use the same tasks. So it's like not apples to apples. So in our kind of data, you'll see, okay, so I'm using this reranker on top of this model on this task. What's the lift in terms of quality? And what's the hit in terms of performance. And by the way, I want to select L4 over here or A100, which is not present anywhere in the benchmark. Like the academic people don't care about latency or like money or, it seems, or it's kind of like maybe hard to collect the data. But, if you are making decisions for sort of like how to engineer your system, this is critical information and we want to kind of have a single big data set that we have to constantly update, of course, as we update the system, new models come in. So this is something that has to be regenerated, every almost every day, actually. So that's maybe like hot take on like if we can generate all the code essentially almost for free, what sort of code does it make sense to keep building and publishing and hoping that other people will find it valuable? And my take on that is that um, like there has to be something expensive about producing the thing that others would find useful. There has to be some kind of bottleneck. Otherwise, they can just replicate it. It's super easy and they don't need yours, right? And in the case of inference, the expensive thing is the benchmarking. So you
Hmm.
have to constantly run the benchmarks, both in terms of quality, am I implementing the models correctly? And in terms of performance, does this meet the targets in terms of throughput and latency? And you have to keep doing that, and you have to do it for a bunch of model task combinations, model task hardware combinations. And so, yeah, we are burning, bunch of GPUs in order to produce this. And that's the kind of work that then you don't have to do when you are planning your own self-hosted cluster and your own deployment.
Nice. Daniel, I've got a selfish question, which is, so I'm most of us who are doing development these days, I didn't say most, a lot of us have Macs for development.
Mm-hmm.
And I also
Mm-hmm.
have like one of those beefy M3 Ultra servers with 512 gigs of unified memory, and so I tend to run local models, like big
Mm-hmm.
ones, sometimes quantized, but I tend to run them and then use some local stuff for swapping and what have you. I'm
Mm-hmm.
curious if this framework has support for non-NVIDIA GPUs or like MLX or things like that, and if not, what your thought is on that. If you're mostly focused on, high scale Kubernetes like in like the cloud and production, or if for sort of,
Mm-hmm.
local deployments, if it works for that.
Yeah, I mean, we are pretty flexible. We have optimized for like all of us at Superlinked have MacBooks, so the local developer experience is optimized for that. And the cloud experience, because you need not the biggest NVIDIA GPUs that are expensive and there is contention for them, but the smaller ones that are much easier to get. Also, spot instances are very cheap. Um, we sort of got away with doing NVIDIA only for now. But if there is demand, it's like not an issue to point the agents
Yeah.
from doing CUDA kernels to something else. Um, and by the way, um, I think having some Cloud Code accounts and Codex accounts, if you are comfortable with sending the data out to a third party, right? is like probably the most cost efficient that you can be. Um, in terms of the kind of high level kind of reasoning and orchestration for the harness. But then the tools are super inefficient. So every time your agent grabs something,
Hmm.
you kind of lost, right? So we have ran a bunch of internal benchmarks for replacing, and there are other teams out there doing kind of semantic grep and like code aware semantic grep and all of that. That's very interesting direction. We believe that agents should be equipped with a bunch of tools powered by small models, embeddings, extraction models, kind of like a Swiss Army knife of models that either run locally if the scale supports it, but if the agent is interacting with a bunch of data, big code base, a lot of documents, then running the models in kind of like a centralized place in your company. Maybe it's like one beefy worker or it's a cluster. If you want to collect a bunch of those small GPUs that are
Hmm.
nicely cheap, right? Then it makes sense to run this as a cluster, and that's the use case that we target with the Kubernetes based
Hmm.
setup.
Okay. Makes sense.
Right.
Yeah.
Yeah, maybe we can kind of wrap it up here. Um, so yeah, please let's connect on LinkedIn or Twitter. I'm just my surname on Twitter. And I'll just repeat the call to action. So we are bringing this inference kind of open source inference product for small models to the market. In 1 or 2 months, or as time permits. We are doing a lot of internal testing, and we are always looking for folks, building cool projects, and if we can help those by sponsoring the inference, or maybe even sponsoring the project kind of more broadly. We would love to hear what we're building, and if we see if we can help.
Awesome. Thank you so much, Daniel. This has been awesome as always. Love having you on. I know this community gets a lot of value out of just hearing you speak and hearing what you're working on. So definitely check it out. And yeah, we'll talk soon. Thank you, everybody. Hope everyone has a great weekend, and hope to see you all next week for the next in this series. We'll be talking about the big deal about agentic search on Monday. So thank you, everybody. Thank you,
All
Daniel.
Looking
right.
forward to it. See
Have a
ya.
good one. Cheers.
Bye. Cheers.